let's do a simple 1D tolerance stackup analysis using worst case study. Okay, start with the new, and our objective is to find out the gap between these two. Okay, and we'll, we'll use we will use the annotation plane as a front assembly. Okay, this is up now in the assembly condition without any tolerances. It's tooling. Okay, let's select the parts. Let's select shaft and then small bearing and the bigger bearing. Okay, and then what it's showing. Okay, and this one. Let's select this face to this. Okay, offset distance. Now things set out. Pairings starting to show. Use one. Phase two. Let's see. Okay. Okay. Okay, let's see what else is missing. That one missing. Okay, this one we need. Okay, let's add that. Let's add this to this. It's there. Okay. It's not showing up. 17 meters come. And then 17, 57, 11 mm. Okay. And then 7. One dimension that's driving this gap. The other one in the bottom loop. 11 is okay. One more 17 is missing. Okay, that is, let's add offset distance. The C bearing 1 to shaft. This one is already there. Okay, let's see that. Okay, let's come. Now let us give the tolerances as per our case study. The first one has a tolerance of plus or minus. This side is 0 and minus side it is minus 1. Okay, let's give the long exit. Okay, and for this 57 dimension, anyway, there goes this key. Plus or minus plus 1, and the minus side it's 2. Okay, and for this 17, it is okay, not symmetric. It is limits. The nominal value, let us do it. The upper is 18 and lower is 17. Okay, and for 11, there is plus sign, symmetric tolerance of plus or minus 1. Okay, now you see the difference. What's happening here, we should give the nominal. Okay, that nominal value should be somewhere in the Okay, let's give a sub now. Something like, it's not 17. If it is 17, then it should be the 1 mm. Okay, let's give 16.5 then. See, should be given plus or minus. That's where we lack. Okay, this is actually the dimension conversion. Okay, we have to do it. That we have done in detail. In another, it's a 17.5 plus or minus 0.5. That dimension. As if it comes, that calculation is given in the detailed video. Okay, so let's take that. Let's take that 17.5. No, it's symmetric. It's 17.5 plus or minus 0.5. Okay. See, okay, it should be 78.48 by its material. Okay, then let's take limits. That also material. Okay, limit. Smooth. Let's limit it. Okay, persons. This should be. Okay. Then we have to make these two arrange in such a way so that this is assembled, this assembly constraint, change it to see that. Okay, rest all dimension tolerances we have set. Let's check once again. It's 17.5% minus 0.5. Okay, let's keep that tolerance applied here. Okay, so that it will exactly match. Okay. Okay, let's close it. And let's go to the assembly. Okay. And let's see this one. Edit the decretion. Let's give this distance 17.5. Okay, save it. And then let's go back to applications. And we are using EZ tolerance analysis. And now let's see that. Yes. Now the worst case analysis says that this gap 12 mm will be at its minimum 8.5 and maximum at 15.5 if we manufacture with these set of tolerances. Okay, that's all. We have completed the worst case tolerance analysis. Thank you for watching this video. Okay, and this analysis is done handmade. We can save it. We can let us see that it is. Let's go to the assembly. Let's go to view and orientation. Let's go to the front and go to the application. Okay, and let's open this, please. Okay, and let us save this value, this view. Okay, let us take this view screenshot. Okay, and generate the report. Okay, save it there. Okay, and this be opening like this, that will be key like this. This is the core objective. This objective has got 8.5. So we should have said that it should be less than or equal to 80. Greater than or equal, greater than or equal to 8.5. Okay, and this is our loop. That 157 is for the, let's say, the loop. This is the dimension tolerance, normal dimensions, tolerances, and the two other. And in the worst case condition, it's 8.5 minimum, 15.5 maximum. Thank you. Thank you for watching this video.